Have you ever stopped to wonder how your phone can find a single contact in your address book, or a database can pull up one specific record in just the blink of an eye? I mean, it really feels like magic, doesn't it? Well, it's not. And today, we're going to pull back that curtain and build the exact data structure that makes it all possible, the hash table. So, seriously, how do they do it? How can a system like a Python dictionary sift through potentially millions, even billions of items and just, bam, find the exact one you're looking for almost instantly? It seems like it should be impossible, right? But it all comes down to this one brilliant and actually pretty simple core idea. In the world of computer science, we have a name for this near-instant speed. We call it O1, or constant time. And what that means is it doesn't matter how much data you have, 100 items or a billion, the time it takes to find one single thing stays on average the same. The secret sauce for getting that O1 performance? You guessed it, the hash table. Okay, so let's get into it. Let's start our quest for that O of 1 speed. We're going to build this thing from the ground up, piece by piece, so you can see exactly how it all works. At its very heart, a hash table is just a super efficient filing system. I want you to forget the idea of searching through every single file one by one. This system tells you exactly which drawer to open before you even start looking. But how does this incredible filing system actually work? Well, it all comes down to a central component, a kind of magic sorting machine that does all the heavy lifting for us. I want you to picture this. You've got a giant shelf, and it's just lined with numbered boxes. This shelf, that's our array. Now, to store an item, you don't just put it anywhere. You feed the item to a special machine, that's our hash function, and it instantly spits out a box number for you. There's no searching, it's just a direct instruction. Put it in box number 5. And here's what that process looks like in a perfect world. It's so beautifully simple. You start with something unique to identify your item. We call that the key. You run that key through the hash function, which crunches it down into a number. That number is your box number or your index. You walk over to that box, you place your item inside, and you're done. It's incredibly fast. So you see, everything hinges on this magic machine, the hash function. Its entire job is to take any key, it could be a name, a number, whatever, and predictably turn it into an index for our shelf of boxes. A really good hash function spreads all the items out nice and evenly across the boxes. But what happens when it's not so perfect? And this right here brings us to the first major real-world problem. You see, our perfect little system assumes that the machine always gives a unique box number for every unique item. But, well, that's not always the case. Exactly. What do you do when you go to put your new item in box number 5, only to find there's already something else in there? This is probably the most critical challenge you have to solve when you're designing a hash table. This little problem has a name. It's called a collision. It's what happens when our hash function, our sorting machine, maps two completely different keys to the exact same location. If we don't have a plan for this, we're going to end up overwriting and losing our data. The most common solution is, thankfully, elegantly simple. Instead of each box holding just one single item, it holds a list of items. So if a new item hashes to box 5, no problem. We just open it up and add the new item to the list that's already inside. This technique is called chaining. Now, while chaining is super popular because it's so straightforward, it's not the only game in town. There's another approach called open addressing. And with this one, if you find a box is full, you just look for the next available one. It can actually be faster in some cases, but it makes deleting things way trickier. So the crucial point here is that there's always a trade-off, usually between simplicity and raw performance. All right, so we've solved the problem of multiple items wanting to go into the same box. But what happens when all the boxes start to get a little too full? The lists inside them start getting longer and longer, and our lookups, well, they start to slow down. To keep an eye on this, we use a key metric called the load factor. It's just the number of items we've stored divided by the number of boxes we have available. Think of it as just a simple percentage of how crowded our hash table is getting. And you can probably see the problem right away. As that load factor climbs, those chains, the lists inside each box, they just get longer. And suddenly our O of 1 instant lookup isn't so instant anymore. Now we have to search through a list, which takes time. We've lost our magic. So how do we fix this? Simple. We get a bigger shelf. Once the load factor hits a certain point, a common number is around 75%, we trigger a resize. We create a brand new, much larger array. usually double the size, and then we have to painstakingly go through every single item from the old shelf and rehash it to find its new correct spot on the bigger shelf. Yeah, it's a costly operation, but it's what keeps our average performance lightning fast. Okay, let's bring all this home. If you're getting ready for a technical interview or you just want the key takeaways, think of this next part as your absolute must-know cheat sheet for hash tables. First up, performance. On average, and this is the key phrase, on average, search, insert, and delete are all of one. Constant time. That's the magic we were chasing. But, and you absolutely have to know this, look at that worst case column. It's O of n, or linear time. This is what happens if our hash function completely fails us and every single item collides into the same bucket. And I really want to hammer this point home, because it's the single biggest misconception out there. Hash tables are O of 1 on average, assuming you have a good hash function and you're managing your load factor. The worst case is a total performance collapse, turning our brilliant filing system into one giant, unsorted, messy list. So, if you're ever in an interview, here are your talking points. You have to mention the load factor and resizing. You have to explain why keys must be immutable. Think about it. If you change a key after it's been filed, the hash function won't know where to find it anymore. And always, always be ready to discuss the trade-offs between collision strategies like chaining and open addressing. And why does any of this matter? Because hash tables are, and I mean this quite literally, everywhere. They're the engine behind Python's dictionaries. They're the core of the caching systems that make websites fast. They're how compilers keep track of your variable names. They're the foundation for so many classic algorithms. Understanding them means you understand a fundamental building block of all of modern computing. You know, we've spent this entire time chasing that O1 speed, but I want to leave you with one final thought. Is faster always better? A hash table is incredibly fast for lookups, but it's totally unordered. You can't ask it for the next item or the previous one. So when might a technically slower structure, like a tree that keeps everything sorted, actually be the better choice? That's a question of trade-offs, and that's what makes this stuff so interesting.